This lecture will be divided in two parts. In the first part, we'll look at the shift left and shift right operations. And then in the second part, we'll look at the bitwise logic operations. Logic operations are very important in systems programming because often we need to do logic manipulation of values that we find in different registers or that we bring in from memory. The first instruction that we'll look at is the shift left logical immediate operator. This instruction is called the SLLI instruction, and it has a source register. In this example, we are using as 0, and it has an immediate value. In this example, is the number 4, and it has a target register. Here we are using T2. So if I assume that the hexadecimal value in S2 is the number 2, which is 2 in base 10, the binary representation of this number has only a 1 in the position of the 2's, so the bit 1 is equal 1. The shift left logic instruction in this slide is telling me that I'll be shifting this number to the left by 4 positions. So after shifting this number to the left by 4 positions, the bit 5 will be equal 1. There will be 4 bits equal 0 that got inserted on the right-hand side of for the least significant bits of the 0. And the 4 most significant bits that were into 0 have been lost. To understand arithmetically what this instruction has done, we need to look at the power of 2 of the immediate. So the immediate was 4. 2 to the 4 is equal 16. So if we take a look now at the mathematical operation that's happening, we can see that we have the number 2 in as 0. In multiplying 2 by 16, we get the number 32. And 2 to the 5 is indeed, 2 to the 5 is indeed 32. So by shifting left by 4 bits, we multiply the number by 2 to the 4, which is 16. Let's look at a second example quickly. In this case, we are shifting left by 2, and we need to remember that 2 to the power of 2 is equal 4. So again, the same operation that we did before, we have the number 2, and in this situation, we are shifting left by 2 positions. So now in my new representation, we have the bit 3 equal 1. And again, 2 times 4 is equal 8, and 2 to the 3 is equal 8. So we have seen that again, by shifting by 2, we did the equivalent of multiplying by 4. In general, if I do a shift left logical by k bits, this is the equivalent of multiplying the number that I'm shifting by 2 to the k. This is actually very useful in many places because a shift operation is much less expensive than a multiply operation. So whenever we need to multiply by integer power of 2, we are much better off using a shift left operation than using a multiplication operation. Another application of shifting is if I want to move parts of the one word to another place in the same word. So let's consider, for example, that I have this 32-bit word and I'm going to divide it into 2 halves, to be the lower half word and the upper half word. And let's say that I give you this question, where I ask you to write the RISC program to move the lower half word of T4 into the upper half word of F2, and I want you to make the lower half word of F2 equals 0. The solution to this quiz would be quite simple. All I need is a single instruction that's a shift logical, a shift left logical operation with an immediate value of 16. Independent of the value that's in T4, what's going to happen is that value is going to be shifted left by 16 positions, and 16 zeros will be inserted in the lower bits of the word, and in this case, I put in the result into S2. Let's say that I have this instruction and I ask what is the value stored in S4 after the execution of these instructions. So initially you may say, well, I don't know what's the original value in T1. But if you look more closely, you're going to see that you don't need that, because you are shifting left by 32 bits, and when you shift left by 32 bits, all 32 bits will be equal to 0. However, in the RAR simulator that we are using in the lab, the number 32 in a shift left logical operation will give you an error, say that the operand is out of range. The shift operation with an immediate uses a modified I-type format. So usually the I-type format will have the immediate in the bits 20 to 31. Because you only can meaningfully shift to 31 bits, you don't need all those 12 bits to specify the value of the immediate. Therefore, 6 bits are reserved for the value of the immediate, and the other 6 bits are reserved for additional opcode field. That's the func6 opcode field. If you attempted to shift left or shift right immediate by more than 31 in the RAR's simulator, it will gonna give an error saying that the operand is out of range. So what happens, sometimes we may not know by how much bits we need to shift the code when we are writing the code. So that's the case where our shift amount is not constant, and is rather the value that's currently stored in a given register. And it's impossible for me to take the value that's in a register and transform it in a constant that I will know when I write in the assembly program. So in this case, for example, I would have an exercise that I want to write a RISC-V assembly code to shift the value of x, which is a variable that I currently have in S3, to the left by k bits, where k is a value that's stored in register S7. So the instruction that I would use for that is the shift left logical instruction. There is no I in this instruction because there is no immediate value. And so this will be an R-type instruction. And in this case, the number of bits to be shifted left is specified by S7. The operation, if I write in a comment form, will tell me that the value of x is shifted left by k bits and then stored back into x. What happens if I do a shift right logical immediate? So the shift right logical immediate will be very similar to the shift left, except that the shifting will happen to the right. Let's say that I have the number 4 in hexadecimal, which is 64 in decimal, stored in S0. 64 will have a single bit equal 1. The bit in the position of the 64s will be equal 1. And I shift it right now by 3 bits, which makes the lower 3 bits disappear, and 3 bits equal 0 are inserted on the left-hand side of the value. So now I have the bit 3 equal 1. So again, if I look at the power of 2 of the immediate value, 2 to the 3 is equal 8. And what I have done is the equivalent of taking the floor of the division of 64 by 8. It's the floor of the division because the least significant digits, those 3 digits that I had in the right-hand side, will disappear. In division operation, those bits would represent the remainder of the division, but in this case I have lost the remainder, so mathematically this is the computation of the floor of the division by 8. And indeed 2 to the 3 is equal 8. So before we look at another type of shift right operation, let's take a little side tour and look at a way that will be very useful in the future. A quick way to find the decimal value of some binary numbers. So let's say, first let's look into decimal. We are very familiar with the decimal number system. If I have the number 999 in decimal, I can express that number as 1000 minus 1, which is 10 to the 3 minus 1. If I have the number 99,999, I can express that number as 100,000 minus 1, which is 10 to the 5 minus 1. But what if I have this number? Well, I can do the same by separating the two groups of 9 and expressing them in the same way. So I can express this number as the number 10 million minus 10,000, and then I can add that to the number 100 minus 1. So this would be the equivalent of 10 to the 7 minus 10 to the 4 plus 10 to the 2 minus 10 to the 0. So let's look at the position of these numbers in the decimal number that I had originally. My most significant 9 was in the position 6, digit 6. And then I had the least significant of that upper group was in digit 4. So notice that in my expression, I end up with 10 to the 7 minus 10 to the 4. And then for the second group, I had digit 1 and digit 0, and I end up with the expression 10 to the 2 minus 10 to the 0. So notice that the first exponent in the first number that I have in the expression here is one more than the position of the digit of the most significant 9 that I had in the number. And the same thing for the second group, I had the most significant 9 at position digit 1, and my power of 10 here is 10 to the 2. We're gonna use the same property in binary representation. So let's say that you are asked to what is the decimal value of the number that's shown in the screen. You could add the powers of 2. You could say that this number is 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128 and so on. But the likelihood that you end up making a mistake by doing that long addition is quite high. So let's see if there is an easier way to find the value of this number using the observations that we just did in the decimal number system. So we're going to observe that that's the bit 14. So we can express this number actually as 2 to the 15 minus 1. Again, the power of 2 is the position to the left of the most significant one of the group. And indeed, if I take 2 to the 15 and I subtract 1 from it, I obtain the number that I had originally there. So now if I want the actual value, remember that I told you that I always know the values of the powers of 2 up to 2 to the 10. So what I'm going to do is break that larger power of 2 that I don't actually know the value into powers of 2 that I know. So 2 to the 15 is 2 to the 10 times 2 to the 5, which is 1024 times 32. And now I can get my calculator and I can get the value for that expression easily without making too many mistakes. So let's look at another example. What's the decimal value of this number? Now I have two groups of ones, so I end up adding two subtraction expressions. And what I need to know is the position of the ones that I have at the beginning and the end of each group. So I have those positions. So my first group of ones can be represented as 2 to the 17 minus 2 to the 10. And the second group of ones can be represented as 2 to the 7 minus 2 to the 2. Now I can do some algebraic manipulation of these powers of 2 to make it easier for me to do my calculation. For example, I can express that as 2 to the 7 minus 1 times 2 to the 10. 2 to the 10 is the common power in those two factors. And again, the second one I can write as 2 to the 5 minus 1 times 2 to the 2. And now I know my powers of 2 up to 2 to the 10. I can simply replace them in the expression, and I can then have a much easier calculation to do using my calculator if I need to, and I will find out that this number is actually 130,172. So this is a way that you can do a conversion from binary to decimal when you have large numbers and you have many ones together in a group in those large numbers. So we can go back to our shift operations, and now we'll do a shift right logical immediate, like we did before. But now the value in S0 is 0xFFFFF0, which, if read as a two-complement number, is the number minus 16 in base 10. So let's see what happens if I do a shift right logical immediate of this number. What's going to happen is that I'm going to shift to the right by 2. I'm going to lose the two least significant zeros, and I'm going to have 2 zeros inserted on the left-hand side of the number. So if I want to know the value of this number now, I'm going to use what I just learned. This will be 2 to the 30 minus 2 to the 2. And again, if I use the same technique that I used before, I can easily find the value of this number, and I'm going to find that it's a very large positive number. So I had minus 16, and I shifted right logical by 2, and now I end up with a very large positive number. So how could I compute, for example, minus 16 divided by 4 and take the floor of this to obtain minus 4? So minus 16 will have that format. And in order to do this, I'm going to need a new instruction. I need a shift right arithmetic immediate. The shift right arithmetic instruction will do the same thing as the shift right logical instruction, but instead of always inserting zeros on the left-hand side, it will preserve the sign of the number. So in this case, the most significant bit of the representation minus 16 is 1. Therefore, when I do a shift right arithmetic operation, I will be again losing the two least significant zeros, but on the left-hand side, I'll be inserting digits that are identical to the most significant digit that I had in my original number. So this way I can compute the floor of minus 16 by 4 and obtain minus 4. So this result is minus 4. So let's do a recap of the shift logic operations. We have learned in this part of the lecture that we have a shift logical shift left logical immediate. And when I do this operation, if I had that was the value that I had originally, what I do, I shift to the left and I insert zeros on the least significant bits. And this is equivalent of multiplying by 2 to the k, where k is the value of the immediate. I have a shift right logical immediate operation that consists on shifting it to the right and inserting zeros on the left. It has no arithmetic meaning because it wouldn't work for negative values. It has the floor of the division by 2 to the k meaning if the number is unsigned. Then I have the shift right arithmetic immediate that correspond again on a shift right shift to the right, but in this case it does correspond to the floor of the division even for signed numbers. I also have non-immediate versions of each one of those instructions. So the shift left logical, I can specify the number of positions to be shifted using registers. The same is true for the shift right logical that I can specify as a value. And I also have a version of the shift right arithmetic where I can specify the number of bits to be shifted using a register. So this is what we had for the shift operations. In the second part of this lecture, we're going to look at the bitwise logic operation.